Okay, this is the lesson for 4.3 and 4.4. This is the properties and laws of logarithms. So what we're going to do today is we're going to figure out what a logarithm is, how we can rewrite an exponent into a log form, also how we can do inverses of log functions, graph log functions, evaluate them, then also expand and condense them. So it seems like a whole bunch, but I think most of it's probably going to be a review for you guys. So we'll start out with rewriting from a log to an exponent. So this is the way logs are written. You've got log base b of x is equal to a. It doesn't have to be the letters x and a and b, obviously, but these are just the spaces that we put them in. So log base b of x equals a is the way that you read that. And we can switch this into exponential form. So that's the point of a logarithm, is being able to go from an exponent into this form so that you can solve for whatever is in your power. So if you have a variable in your power, you want to write it in log form to be able to solve it. Okay, so going from log to exponential, this is how we do it. We write the base is going to be our base. The number over here by itself is the power, and then that is going to equal x. So if you see an exponent written in this form and a logarithm written in this form, they are mathematically equal to each other. That's the exact same thing. That means the same thing. Okay. All right, so one way that I remember how this goes in the order that it goes in, I start with my base, I swoop over to the a, and then I come back here. Okay, so base to the power equals this number. I always double check that. So I'm going to do an example where we go from log form to exponential, and then I'll do an exponential back into log form. So two examples here. First one, we're going to write log base 2 of 32 equals 5 into exponential form. So I'm just going to go in the same order. 2 to the 5th equals 32. Log form, exponential form. Now I'll go the other way. That 4 to the 3rd equals 64, and I want to put it in log form. I know it's log base 4 because the base of my exponent is 4. And then I have to decide, does the 3 come next or does the 64 come next? So you always want to think, let's see, the power's over here by itself, and that's the number that it equals. So this would be the number that it equals, and then the power is over on its own. And then you can double check. I always do my little loop swoop around. 4 to the 3rd equals 64 after I get my answer, just to make sure that I'm good. Okay. All right. So the next thing that we are going to do is we are going to write the inverse of a logarithmic function. Logs and exponentials are inverses of one another, if you haven't noticed. But we are going to, I'll show you exactly how to do it if you've got a log function and you want to write it in exponential form. So for, not in exponential form, to write it as an exponent or to write the inverse. Here we go. So remember, for inverses, we're going to switch x and y. Then we'll solve for y. So that's our goal. So I'm going to write a function out. We'll switch x and y, and then I'm going to show you how we can actually get y by itself. So here's our equation. Let's say we have y equals log base 2 of x minus 4. And I want the inverse of this. So I want to switch my x and my y, and then I want to get the y by itself. So we have to use some of what we just looked at, or switching into exponential form, to be able to get the y alone. So let's go with our first step, trade our x and our y. So x equals log base 2 of y minus 4. And right now I want to get the y by itself, but I can't just move things out of these parentheses because this is an operation. This is telling us to take the log of y minus 4. So in order for us to get the y to where we can solve for it, we have to rewrite this as an exponent. So this is, I'm going to put a little star here that says we need to write as an exponent. Okay. All right, so I'm going to do that, and it looks like that my base is going to be 2. It's going to be raised to the x. That's what it's going to be by itself. It kind of looks a little different because it's not on this side where we're normally used to seeing it. But you can just think about putting the equals x on that side. 2 to the x is equal to y minus 4. Then if I want to get the y by itself, all I have to do is add 4 to both sides, and then you get the y alone. So plus 4, and y equals 2 to the x plus 4. So that is the inverse of this function. So if we were to graph 2 to the x plus 4 and switch all of our x's and y's, we would get the log function there. Okay. All right, the next thing that we are going to do, we're going to evaluate some logarithms, and I'll show you how to do that. Evaluating logs means we're looking for the power. We want to figure out the base to what power gives us the number that is written there. So if I have log base 3 of 9, I'm trying to figure out 3 to what power gives me 9. So that's what's going on in my head. 3 to what power is equal to 9? And I know that 3 to the second power is equal to 9. So 3 to the second is equal to this. So you're always looking for what power should go there. Okay, we'll try another one. Let's go with log base 25 of 5 equals blank. So 25 to what power is going to give us 5? So 25 to blank equals 5. Well, it's going to have to get it smaller. And I know that the square root of 25 is 5. And if we remember, the square root as a power is 1/2. Remember, 25 to the 1/2 is going to give us 5. Numbers on the bottom are roots. Numbers on the top are powers. We'll try one more of the evaluating. Let's go log base 1/4 of 16. So we're thinking 1/4 to what power is going to give me 16? So I know that 4 squared is 16, but I want to get the number from the bottom of the fraction to the top of the fraction. And remember that we can switch sides if our powers are negative. So just a reminder that 4 can jump up to the top if we have a negative exponent. Same thing if it was on the top and needed to go to the bottom. So we're going to have the exponent of -2. 1/4 to the -2 is going to give us 16. So that is evaluating some that you can do in your head. If you're going from bigger numbers to smaller numbers, you need fractions. If we're going from a fraction to a whole number or vice versa, you're going to need a negative in your answer. Okay, so the next thing that we're going to do is we're going to look at some common properties that get used all the time, so we need to be familiar with those. They're just some properties of logs. We have some identity properties, some properties with powers that we just need to make sure that we know. So this is the first one that we see a lot, that if we have log of 1, it doesn't matter what the base is. Any number to what power is going to give you 1. And remember, that is the 0 power. So anything to the 0 power is going to give you 1. So if you see log 1 in any form, your answer is just going to be 0. If your base and the number you're taking the log of, if those are the exact same thing, if they match, we know that we could say that a to what power is a? That's going to be the first power. So anytime that those match, your answer is going to be 1. scoot this up so I can scroll down. Won't let me scroll down. There we go. Maybe not. Sorry about this. Okay, so our next property says that if we have got log base a of a, and then that's raised to some power, whatever that number, whatever that is raised to, is just going to be what our answer is. Because if we think about it and think about the way this is written, and if we were going to rewrite it as a power, a to what equals a to the x? Well, a to the x equals a to the x. So if these two match, whatever your power is up here, that's just going to be your answer on that side. And then in the same way, if you have a base that matches your base here, we're up in the exponent, the x is just going to be what we have there as well. Because if you wrote it as a log, log base a of x equals log base a of x. So those are 4 of our basic properties. We'll also look at our common logarithms. Common logs means we use them so much that they have their own special property. And the first one is base 10. If there is no number that is written here, it's an understood base 10. So if I had something like log 100, I'm going to assume that there is a base 10 there. So no written base is the assumption of a base 10. So this actually, 10 to what power is 100? That is 2. So there is an understood base 10 if there's not one written. And our second common log is base e. If you have it written as ln, this stands for natural logarithm. Natural logarithm. That has got an understood base e. Okay. So ln of x, that's the same thing as log base e of x. So ln and log base e, those match. We just use log base e so much that it gets its own special name. Okay, so when you see it, don't think, oh, I don't know what this means. You do. It just means log base e. Okay, I'll do a couple examples that go through these properties before we go into expanding and condensing our logarithms, and then we'll see about a graph or two. So log base 4 of 4. 4 to what power is 4? That's going to give us 1 for our answer. And we can look up here, these two match, so our answer is going to be 1. Log base 4 of 1. Well, log of 1, doesn't matter what the base is, it's always going to be 0. Log base 4 of 4 squared. When these two match, it all just goes away. We are left with a 2 for our answer here. Again, 4 raised to the log base 4 of 7. When these two are the same, they're going to cancel each other out in a way, and our answer is just going to be 7. Log of 1,000. Remember, if there's not a base written, it's understood to be 10. So 10 to what power is 1,000? Well, remember with tens, you can just count the zeros. So 10 to the 3rd power is going to give us 1,000. This one comes up a whole bunch. The natural log of e. People think, oh, I don't know how to figure that out. But you've got to remember that this ln just means log base e. So I'm going to rewrite that as log base e of e. And then you'll see that these two match. And it's just like the one we did at the beginning. So base e of e, that's going to be 1. Okay? And one way that I remember, I think it's just kind of silly, that log ln of e is 1, is I always just make this into an O and then it spells the word 1. I know that's kind of ridiculous, but it helps me every time that I do those problems. Okay. All right, we have 2 more little examples. Let's go with e to the ln of 4. This is in the same way related to the one that we just did. This is a log base e. When those two match, will just be 4 for our answer. And the very last one, if I had natural log of 7.5, well, I wouldn't want to try to do that one in my head. You will push the natural log button in your calculator. It is on the left-hand side. You'll see the letters ln. Just hit ln 7.5, and it looks like I've got 2.01 for my answer. So that was a calculator problem. Okay. All right. How about let's just go ahead and do the graphs, and then we'll do our expanding and our condensing after that. Graphs, that's not how you spell it. That's fun. That's about how today's going. Graphs. The graphs of our log functions, if we'll remember, I told you they're the inverse of the exponential. And inverse would mean we would switch our x and our y values and shift them around. So I'm just going to remind you what 2 to the x looks like. So this is just a rough sketch, just so you can see it. Remember that this is y equals 2 to the x. It's a growth function. It goes through 1. That's 1 right there. So an inverse is going to be a reflection along the y equals x line. Okay, so all of our x's become y's, all of our y's become x's. So we could plot these points if we wanted to, but I'll just show you just a rough sketch of what this is going to look like. This 1 here becomes a 1 here. Our horizontal asymptote becomes a vertical asymptote. And our graph looks like this. Okay. So our inverse of 2 to the x, we could rewrite this as a log. It would be log base 2 of x. So this is one of our main log functions, but we should note that we have an asymptote that is vertical rather than horizontal. That our domain is from wherever your asymptote is, greater than that, if it's in this order, or if it's less than that, if it's reversed, then our range is all real numbers. Okay, so just a reminder, we can write that down. Our domain for this function, x is greater than 0, the range is all reals, and we have an asymptote that is horizontal, goes through the line x equals 0. Not horizontal, sorry. This is vertical. The asymptote would be shifted if your graph is shifted left or right, or not if it's up or down. Just if it's shifted left or right, your asymptote is going to switch. But your transformations are the exact same as your transformations have been before. If it's with the x, it's going left and right. If it's a number at the end, it's going up and down. So you're taking this picture here, this graph here, and switching it around. So if you know this is the original one that you're dealing with a growth function, you'll know how to switch all of that. So I'll just write down your basic transformation form so you can have that. So our plus k at the end, remember, that's going to shift it up and down. The x minus h, that's going left and right. The a in the front, it's going to stretch or compress, and if it's negative, it would flip it upside down. Okay, remember, a left is going to be positive, a right is going to be negative. So you do have a couple problems in your homework where you are looking at the graphs. Really, you just have to look at the transformations. This is the original graph for log base 2 to the x. You're just moving that around. Which ones would move it left, right, up, down? Okay. All right, so the next thing that we are going to look at is the expansion and condensation of your logarithms using our laws of logarithms. We have a product, a quotient, and a power law, and we use those to combine them and also to expand them. Okay, so here we go. These are our laws of logarithms. We have product, quotient, and the power. So our product law says that if you have a log base a of two numbers multiplied together, you can separate those into two separate logarithms. So here it is formally written. Log base a of x times y, that's a product there, can be split into two logarithms. Log base a of x plus log base a of y. So if it is a times originally, it would switch into a plus. This has to do with the properties of exponents. If I had x to the 5th times x to the 7th, we add the 5 and the 7th together and we get x to the 12th. Since our logs represent powers, that is the reason that the times turns into a plus. Right? So for an example, if I had log base 4 of 3x, I can split that into log base 4 of 3 plus log base 4 of x. Right? Our quotient property. Our quotient property is going to be dividing rather than multiplying, but very, very similar. Okay, so our quotient, we've got log base a of x over y. So that would be log base a of x minus log base a of y. So the dividing turns into a subtraction. Just like the product property had to do with the exponent, same thing with the quotient. If I had x to the 10th over x to the 8th, I would subtract those numbers and get x to the 2nd. So very similar. All right, we'll look at one real quick. If I have log base 6 of 10 over, I don't know, 3, that's the same as log base 6 of 10 minus log base 6 of 3. We can also go in reverse. So if you have a subtraction problem, you'll combine those together to make a division, 1 log, and it's going to be division. If you have plus, you'll combine those together to 1 log to make a product there. Okay, power property is our last one. This is my favorite property. I think it's just kind of fun to do. So if I have log base a of x to the y, whatever you have in the power can just get shoved into the front. So our power here should just get stuck into the front, and that's the same as y times log base a of x. So this number in the front can go, it can just kind of hop back and forth. If you have a number in the front, you can make it a power. If you have a power, you can put it down into the front. Okay. All right, so an example of that is if I had log base 5 of 3 to the 2nd, that's going to be 2 times log base 5 of 3. We're going to go ahead and use all of these properties, combine them all together, and expand and condense our logarithm. So expand means take them from a single log and make it into multiple. Condense means to take multiple logs and combine them into one single logarithm. So we'll start by expanding. We're going to use multiple properties at once. Add log base 4 of x to the 3rd, y to the 7th. I've got a combination of product and power. So I'm going to go ahead and do the product part first. So log base 4 of x to the 3rd plus log base 4 of y to the 7th. It was a time, so I'm going to switch it to a plus. And then I notice that I have these powers that are here, and I want to go ahead and move them down to the front. This will be 3 log base 4 of x plus 7 log base 4 of y. Okay, when you're expanding, you don't want there to be any powers left, and you want each variable to have its own separate logarithm. Okay. Our second example for expansion, we have log of xy over the square root of z. We've got a product, and then we also have a quotient here as well. So I've got log, I'm just going to split this up into log xy minus log root z, and then I will split up the multiplication here into two logs. Remember, multiplication represents a plus when you split it. Log x plus log y, then minus log square root of z. But remember that z, the square root is really just a 1/2 power. So I'm going to write that as a 1/2 power. And then remember that I don't want the 1/2 to stay. I'm going to put that in the front. So anytime you see a 1/2 that's in the front and you think about moving it up as a power, that's going to correspond with a square root. We've got log x plus log y minus 1/2 log c. And so if you see the 1/2, that is going to be the square root in your answer. So now we're going to combine logarithms together. So we just did an expansion. Now we're going to condense or combine. You can see it written in different forms. So to condense them together, I'll do a natural log problem. Let's say I had ln of 7 plus ln of x minus 3 ln of y. So we have a multiply, we have a divide, and we've also got a power that's in the front. So if we can think about it, this is going to turn into ln of 7x, because plus means times. I'm going to go ahead and keep my minus. And remember, the numbers in the front can hop up to a power. So that will be ln of y to the third. Then a minus means that we will divide. So we'll have ln of 7x over y to the third. You are done in your condensing problems when you just have one logarithm left. Okay. A lot of you guys could probably do that in your head. Notice, okay, 7x will be on the top and y to the third will be on the bottom. And that's perfectly fine. You don't have to write anything down for this assignment. And our last thing that I'm going to show you how to do is how to evaluate your logs in the calculator using change of base. So really, change of base, this is how we do the logs in the calculator if they have the log notation disabled, which I know all the ones at school do. So if I've got something like log base 2 of 14, and it's not something I can figure out in my head, I don't know 2 to what power is 14, it's not a whole number, it's bigger than 3 but less than 4 just because I know the powers of 2. But if you're not certain and you know it's going to be a decimal, this is how we're going to write this to figure it out in our calculator. We're going to say log of whatever you're taking the log of here, divided by log of the base. So these are both base 10, and base 10s are the ones that are in the calculator. So I just take my calculator and I type in log 14, close the parentheses, divided by log 2, and I get 3.807. So if you see a log and they're asking you to get the answer and the answer's in decimal form, no, you're going to do it in the calculator, log of this number divided by log of the base. The log of the base is always on the bottom when you're doing change of base. Okay? Well, hopefully that didn't go too fast in this video. I didn't want it to take a whole bunch of your time. And that you remember some of the stuff that you did in Algebra 2. Remember to ask me questions if you have it. And since you did have to watch a video, I am going to give you just a little bit of extra time on your homework. So it's not due until Friday instead of the normal Thursday due date for this.